Okay. So yesterday we revisited chapter 3, right? I talked about the Titanic example again because contingency tables relate very heavily with conditional probabilities. In fact, what we did with contingency tables is exactly the same thing as what we're doing with conditional probabilities. It's just now with conditional probabilities, we're giving it some formal notation. The other greatest hit from chapter 3 was discussing the idea of independence. Can somebody just tell me really quickly, raise of the hand, what do we remember of what independence is? Like a general definition. It's when two things don't affect each other, right? So if we have two different variables, they are independent if they are not influencing each other in some way, okay? And independence is a very important question in statistics that we should answer because ideas about representation and even a lot of crimes detectives and stuff like that use ideas of independence to try and solve things. I don't remember if I told you guys the story when I was a couple years ago. It was like my second year teaching statistics. I have a buddy who moved to Arizona to work immigration there. He works border control down in Arizona. He's a private investigator, and he uses statistics to try and solve crimes that of like drug dealing across the border. What he does is he follows bank accounts and he follows the money, and he uses two main ideas: the idea of independence, following two variables to see if what is it? It's like the money moved is independent of something else, like some other money being moved. I don't remember exactly, but he also uses some scatter plots and correlation, which we'll talk about later. And he calls me every once in a while to ask me specific questions. So I don't mean to brag, but I've solved crimes down in Arizona through my consulting work with the U.S. government. I don't like to talk about it though because I'm kind of like that guy from Numbers, you know, like I sit in my office and I run my math and I solve crimes. So I'm basically a detective with my day job, right, is teaching the math. But I've been consulted by the U.S. government, you know, all the time. So, yeah, all the time, like twice in 6 years. So, okay, so independence of two events means that the outcome of one event does not influence the probability of another. Okay, so to state that differently, the outcome of one event does not influence the probability of another event. And if we wanted to write that in the probability notation, we get this thing right here. Knowing what we know about conditional probabilities, this little formula right here represents what, that was supposed to make a line. There we go. That little formula right there represents exactly what we mean by independence in terms of conditional probability. So let's just read that notation in English, okay? The probability of event B, given that A has occurred, is the same as the probability of B. So notice what we're saying here is that if I know that event A has happened, what's the probability of event B? And is that the same as knowing the probability of event B happening without any information about A? Because if these two probabilities are the same, then they don't influence each other. If I know that A existed, and the probability that B happens is the same as the probability of B happening without me knowing A has happened, then they're independent. Okay? If foreknowledge about event A changes the probability of B, then they're not independent. But if foreknowledge of event B is the same as the probability of B, does not change the probability of event B, then they are independent because those two things are the same. Right? If I know that event A happened and that changes my perception or probability of event B, then we lack independence. If it does not change my perception or probability of event B, then there is independence. It means that A is not influencing B. So we can use that information to solve problems now. If we know the probability of B happening and we know the probability of B happening given that A has happened, we can determine if two things are independent. Let's just answer a quick question, okay? This is the same on-campus information that we started on day one, okay? 56% of college students live on campus, 62% have a meal plan, 42% do both. Are living on campus and having a meal plan independent of each other? Meaning, if I know that somebody lives on campus, does that change the probability that they have a meal plan? Or vice versa, if I know that somebody has a meal plan, does that change the probability of them living on campus? If those two probabilities are the same, then there's independence and one does not influence the other. If they're not the same, there is not independence, and knowing information about whether they live on campus will change whether or not we think they have a meal plan. So let's calculate it. We need to find out, does P of meal plan given on campus, does that equal P of meal plan? So again, in English, representing that information, does the probability of having a meal plan, given that I know they live on campus, change the probability of whether or not they have a meal plan? Okay, so what information do we know? We don't know this yet. What's the probability that they have a meal plan? 62%, 0.62. Okay, so that's 0.62. We need to calculate this one. Let's use the conditional probability formula to do that. P of meal plan given campus is the same as P of meal plan and campus over P of campus. So what's that information? What's the probability of meal plan and campus? 0.42. Right? That's given here. They do both. What's the probability of living on campus? 0.56. And we're saying if they're independent that those two things should be the same. So somebody, can you do 0.42 divided by 0.56? No, can't? 0.75? Yeah, I just couldn't hear you. Sorry. So, are these things independent? No, they are not. No. There is evidence. And notice how I'm not saying no, they're not independent, because that would be really definitive of what we're saying, and we try not to be definitive when we're giving results and statistics. We're saying no, there is evidence that living on campus influences having a meal plan. And I know that there's evidence of them living, that there's influence happening there, because knowing that somebody lives on campus increases the probability that they have a meal plan. If I randomly choose a person and they tell me that they live on campus, there's a higher likelihood that they have a meal plan than if I didn't know that. And because that changes it, there's a lack of independence. There's influence going on. You're more likely to have a meal plan if you live on campus. And honestly, it kind of makes sense in this case because people who live on campus, they can't make it out. Most people who live on campus on colleges don't have a car. They have a bike, and it's not fun to go to the grocery store on a bike. So they tend to have meal plans because it's easier. Questions about independence? We've talked about independence before. We did it with the contingency tables before, but this is like the definitive, actual mathematical definition of independence and how we calculate it. So is there anything else we need to say about that before we look at tree diagrams? Okay. Oops. Okay. I don't want to do this problem. Is this one on your notes? None of the stuff on independence is on your notes? It's the stuff on independence. What's that? No, it didn't. You can tell because the volume of my voice is sometimes I feel like last year Jason was like high or something. Like, what was I thinking last year by creating notes that are totally different from my slides? So. No. Like, there was a lot of stuff that I didn't put in the notes. So this hopefully should be where we start talking about tree diagrams. A tree diagram helps us think through conditional probabilities by showing sequences of events as past that look like branches of a tree. Hey. What if I had a day where I was like, nope, I just don't feel like doing that right now, and then that day never came. Every year I feel like, what an idiot teacher I was last year. What was I thinking? Hopefully, I think is what we can say about that. Okay, so a tree diagram helps us think about conditional probabilities by showing the sequence of events as paths that look like branches of a tree. Making tree diagrams for situations with conditional probabilities is consistent with the make a picture mantra, right? It's going to be extremely helpful for the things that we're going to do tomorrow, which is called reversing the condition. And having a tree diagram is going to be infinitely helpful for you. So let's make sure we can draw to you tree diagrams fairly well. So, according to a study by the Harvard School of Public Health, hopefully this example is in there. Yay! 44% of college students engage in binge drinking. 37% drink moderately, and 19% abstain entirely, right? In binge drinking, you should think of as the same as like binge watching something on Netflix. You just drink a lot. You're not like, yeah, it's alcohol poisoning is what it is. This was an in general. This is college students in general engage in binge drinking. So this is like every Friday night, 44% of college students just get smashed, right? Sounds like college. Another study published in the American Journal of Health Behavior finds that among binge drinkers, so given that they're a binge drinker, 17% have been involved in an alcohol-related car accident, while non-binge drinkers of the same age, only 9% have been involved in such accidents. That would be drinking moderately or abstaining entirely. If they were in the same car, I believe that would be under the 17%. If you're thinking that the non-binge drinkers are getting in an alcohol-related accident because they're going with binge drinkers. Um, correct. I would think of this as just one person in the car. Otherwise, you're going to way overcomplicate the problem. Okay, so we have a tree diagram of of the situation. That's what that tree diagram there is on the right. So what a tree diagram is you are drawing branches of a tree based on the different events that you have. So in this particular example, we have two different events. We have whether or not a student is a binge drinker, moderate drinker, or abstains from drinking. And the second event is whether or not they've been in an accident or whether or not they have not been in an accident. Now, a couple things to notice about this particular tree diagram. First of all, or tree diagrams in general, I should say. First of all, we labeled all of our branches and we've given a probability of each of those branches. Okay, so this is based on the problem stem. The probability that you're a binge drinker is 44%. So going up this path, the probability you're a binge drinker is 44%. The probability that you're a moderate drinker is 37%, and the probability you abstain entirely is 19%. That's where those numbers come from. And again, it's important to label those things on there because the way we find these other probabilities, we're going to use those things. So now let's go up one of the branches. Given that I'm a binge drinker, right? Notice that as I go up this branch, what I just said, given that I'm a binge drinker, all of the things up here are a conditional probability. I am knowing background information that I am a binge drinker, okay? Given that I'm a binge drinker, the probability that I've been in an accident is 0.17. So this probability right here is the probability that I've been in an accident given that I'm a binge drinker. Right? That 0.17, that's what we said earlier. Given that I'm a binge drinker, the probability I've been in an accident is 0.17. That means that this 0.83 down here is the probability that I've been in an accident, given that I am not a binge drinker, right? So I'm going to write binge drinker complement. Binge complement. So we can see the conditional probabilities inside the tree diagram. Given that I'm a binge drinker, that's 0.44. There's a 0.17 chance that I've been in an accident. Probability I've been in an accident, given I'm a binge drinker. And the probability that I've been in an accident, given I'm not a binge drinker. And that probability is 0.83. Notice that these two things are complements of each other. Jarrett and Brady. Oh yeah, you're correct. I'm sorry. That should be accident complement. And yes, you're right. Given that I'm a binge drinker, I have not gotten into an accident. I apologize. Thank you very much. Brittany, what were you going to say? Okay. So then what's this last probability over here? What's 0.075? You might notice that if you multiply 0.44 times 0.17, you get 0.075. That's one. I don't know. Maybe somebody did the multiplication, right? I don't know. But what is what in terms of our notation? What is that 0.075? Can you have a 30-second conversation with the people around you to try and figure out what that one is? What is the 0.075? In terms of our notation, right? Write the notation down. Okay, let's hear it from somebody. Lane? Equals 0.075, right? This is the probability of binge and accident, and hopefully you notice that follows our conditional probability formula, right? Because remember, conditional probability formula was P of A and B equals P of A and B over P of B. Yeah, okay, let's make sure I did that right. But if we were to solve for P of A and B, we would multiply both sides by P of B. So that's P of B times P of A given B. Well, that's what this is. P of binge drinker. This 0.44 is P of binge drinker. P of binge drinker times P of accident given binge drinker is the probability of P of binge drinker and accident. P of binge drinker times P of accident complement given binge drinker is P of binge drinker and no accident, or accident complement. Are we seeing the connections between our probability and the tree diagram? That's the most important part. Do we understand where those are coming from? Anytime we have multiple events, dependent events, not independent, dependent events, we can create a conditional probability tree chart. So let's make a tree chart to answer these two questions. What is the probability of drawing 2 spades in a row from a deck of cards? This is a conditional probability because when I draw a spade from a card, or excuse me, when I draw a card from the deck, right? How many cards are now in the deck? 51, right? That's a dependent probability because knowing that I've drawn a card, no matter what it is changing the probability of the second event. Dependent, okay? In fact, if I know the first one is a spades, that changes the probability of the second event even more because now not only are there 51 cards in the deck, but there's also less spades in the deck. We have a dependent probability here. And so we're going to draw a tree diagram to represent it. So, first event, we are going to draw a card. We are asking ourselves to figure out 2 spades in a row. So, first draw of the card, what are the 2 possibilities that I can have here? Spades and not spades, right? So we got spades or not spades. What's the probability of spades? 0.25, it's 1 in 4, because there's 13 in the deck, right? So the probability here is 0.25. The probability of not spades, therefore, is then 0.75. Okay. Given that I've drawn a spades, what are the next 2 options for the second draw? It's still spades and not spades, right? But now our probabilities have changed. Given that I've drawn a spade, how many spades are there in the deck? 12. How many cards are in the deck? 51. So this probability is now 12 over 51. And let's just get a decimal for that. The decimal is easier to work with. 0.235. Okay? So, given that I've drawn a spades, the probability I draw a second spades is 0.235. So, what's the probability that I draw spades and spades? Because that's the only way that I can draw 2 spades in a row, right? What's the probability that I draw spades and spades? 0.25 times 0.235, which equals 0.88. 0.0588. Notice that we actually didn't have to fill out the entire tree diagram for this, right? I just went down the tree branch that I know I had to go down. spades and spades. The only possibility of drawing 2 spades was to go spades and spades. So I didn't bother calculating the rest of these. We could, right? Spades and not spades. This is going to be the complement of 0.235. 1 minus 0.235 is 0.765. That would be, I drew a spades on my first draw, and I drew a not spades on the second draw. This would be, I drew a spades on the first draw, I didn't draw spades on the second draw. This would be spades on the first, spades on the second. This would be no spades on the first, spades on the second. This would be no spades, no spades. And we can find those ones, but I'm not going. Okay, let's do the bottom one. What is the probability of it drawing exactly 2 hearts in 3 draws? If I have 3 different draws, how many different ways can I draw 2 hearts? What's one way that I could draw 2 hearts? Heart, heart. So I'm just going to call it heart, heart, not heart. What else could I do? I could do heart, not heart, heart. Okay. What else could I do? Not heart, heart, heart. What else could I do? That's it. No. So in order to accurately figure out exactly 2 hearts in 3 draws, I do have to go down multiple branches on my tree this time, because I have to figure out this one and this one and this one. There's 3 different ways to do it. So let's draw a big old tree, okay? We're going to have draw 1, heart, or no heart. Then we're going to have draw 2, heart, no heart. And then we're going to have draw 3, heart, no heart. And notice that draw 3, there's a couple different probabilities or a couple different possibilities for all of these. Notice that also tree diagrams can get messy real fast. Really fast can they get messy. Let's just calculate the ones that I need. The ones that are exactly 2 hearts. I don't want to go through all this extra work. So, hearts, hearts, no hearts. I need this one. I need hearts, no hearts, hearts. Hearts, no hearts, hearts. I need this one. And then I need no heart, heart, heart. No heart, heart, heart. Those 3 branches are the only ones that are exactly 2 hearts in 3 draws. I calculate those 3 probabilities, I add them together, I get my solution. Go ahead and do that. Watch your head, Hannah. Nope. No. If I was trying to kill Hannah, I wouldn't have warned her that a pen is coming at her.
Maybe you like a challenge. I don't know.
I'm going to kill you tomorrow. Just so you know.
Get a heads up.
That's a heads up. That way you can protect yourself when I come to kill you. Because I like some sport.
I like right challenge.
Yeah. Oh, yeah. So what I meant by that in terms of probability is that there's a dependent relationship between the given condition that you know that I'm going to kill you versus actually it's independent because I'm going to kill you no matter what you know, even if you know the same probability of you dying. Well, then get better at life. I'm going to stop the recording now. Nope. I'm discarding that. Hi.